So I thought that it would just be quite helpful to have a kind of a recap on surface integrals. So specifically, firstly looking at surface integrals of scalar fields, and then having a look at surface integrals of vector fields. So to start off pretty simple, sometimes we want to take some scalar field, which we're calling them scalar fields now, but you can think of it just as a function of x, y, and z. And we want to integrate it over some surface. So essentially what we've got is some surface like this thing over here, and over that surface we want to integrate whatever this function is. So in order to actually get any further than that, we know that integration we need to have little surface elements. So we need to know, if you like, what a little ds is, and then we need to integrate over all the little ds's. And the way that we look at that, we do that in this case, is we usually parameterize the surface. So remember, we learned how to parameterize curves. Well, we can also parameterize surfaces. So in this case, if we're parameterizing a surface, we have two parameters, a u and a v. So basically, we have our vector r, which depends on our two parameters u and v. So when we had only one parameter, we were using t, but here we're using u and v. And for every pair of values u and v, we get out of our parameterization a value of x, y, and z. Then it turns out, and you can go and check the notes because we talked about this a little bit more, but if you want to work out what your little area element is here, if we look at it a little bit closer with our parameterized version, our little area element, which we're calling ds, is given by the magnitude of the cross product of the two little tangent vectors that we can construct based on our parameterization. Okay, so there's a lot going on in there. Go back and recap on how you find tangent vectors, finding the cross product, and it turns out that the cross product of two vectors gives the area of the parallelogram which they construct between them, which is exactly what we want here. So just to clarify, our two tangent vectors, our dr by du and dr by dv, they look like this. Okay, so we've just taken for dr by du, each component, our x, y, and z components, each get differentiated with respect to du, and the same for dv. So if we take the cross product, we get this crazy looking thing over here. So this is, I've spread it across 3 lines here. So in the textbook, they use slightly different notation. So they will call this thing in the textbook, I think they call it something like duz by duv, something like that. I find that complicated. So I'm just going to refer to this whole thing here as A, and this whole thing here as B, and this whole thing here as C. And so once we've taken that cross product, we actually need the magnitude of that. So here we've taken the magnitude, and our magnitude is just going to be the root of the squares of each of those components. So there's my A and my B and my C. Okay, so finally, what does this give us? This says that for our parameterized surface, if we want to find the value of this little area bit there, in terms of our parameters, then what we need to do is we need to calculate this thing over here. And why do we want to do that? Because now we've got parameters, so now we can take this integral, which we had all the way up here, which was not very clear, we didn't really know what to do, and we can turn it into a double integral in terms of u and v, and we know how to do double integrals. So the whole purpose of this whole thing was to take an integral over a surface that wasn't clear how to do and convert it into a double integral in parameters which we know how to do. So this is all still pretty abstract because we've just got some parameterization, but most often what we have to do is handle a simpler situation where we want to integrate our scalar field over some surface, but it's written as z is equal to some function of x and y. So in this case, we can kind of think of our parameterization as saying, well, x is equal to u, y is equal to v, and z is some function of u and v. So we're going to basically work through and find our volume element in this case, but we're going to have it in terms of x's and y's instead of u's and v's. Okay, so if we have a look at this over here, so here's the thing that we've got. We've got our surface, S, and we've got some function f that we don't really know about, that we're not too particularly interested in. We just want to integrate it over the surface S, which in this case is parameterized as g of xy. So you can think of the surface as being something like, I don't know, z is equal to x squared plus y squared, so a nice paraboloid or something like that. So we are, if you like, parameterizing that surface in using x and y. We don't often think of x and y as parameters, but they absolutely are. Okay, so what does this do for us? So if we've got this, then our parameterization is really saying that we can find any point on our surface, so our r can be written as, let's see that I get this, u, v, g of uv. So that's just using this parameterization that I've got over here. So I'm turning things into u and v, and then you'll see at the end we're going to go back to x's and y's, and we'll have our volume, our surface element that we want. Okay, so I can now work out my dr by du, which is going to be, well, in this case, so remember dr by du, so I take each element of my r and take the partial derivative with respect to u, so that's going to give me a 1, just v du is 0, and then I'm going to have dg by du, and then I'm also going to need my dr by dv, which is going to be 0, 1, dg by dv. And this means that I can work out my volume element, my surface, my area element ds, which we know is dr by du, dr by dv, du dv. So that's just straight from what we were talking about up here. But now I can work out explicitly, because I have my dr and dv, my dr by du and my dr by dv. So I can work out this. How am I going to do this? Okay, first I'm going to work out the cross product. So I'm going to work out this thing here. Okay, so we know that this is the determinant of I, j, k, and now I need each of the elements. So I've got 1, 0, dg by du. Here I've got 0, 1, dg by dv. Multiply that all out, and what do I get? We get, so the I direction, we get a, so we take this direction first, that gives me 0 in that direction, and now going back in that direction, so I get a minus dg by du in the I hat direction. Same thing happens in the j direction, I get a minus dg by dv, the j direction, and in the k direction I get a plus 1k. So now I need to take the magnitude of that, so my magnitude of this thing it's just I'm going to square each of those components, so I end up with dg by du all squared plus dg by dv all squared plus 1, because I've squared each of those components. So finally, out of all of this, if I have a surface that is parameterized using x and y, instead of having to do this whole complicated crazy thing that I had up here, where remember our a, b, and c were all of these things here, if I'm parameterized with x and y, this whole example here is telling me that my area element is just ds is equal to this thing here and du dv. But if you go back and remember up here, x is equal to u and y is equal to v. So in fact, what this is really telling me is that if I'm parameterized in this way, I can just find my area element by taking dg by dx, dg by dy, and having dx dy. Okay, so this is kind of a simplification, but it happens to be a situation that we use often. So the most general form is this crazy thing that we did up here, where you've got any old parameterization. But if you have the nice parameterization that we often have, where your surface is expressed in terms of x and y, then what you end up with is an area element like so. So let's have a look at an example. Okay, so suppose we want to evaluate this surface integral here. So we've got our function f of x, y, z here is pretty straightforward. It's just f of x, y, z equals y. And the surface over which we want to evaluate this function is given by this surface here, which we can write as g of xy is equal to x plus y squared. And we want to evaluate it over the area where the surface is bounded by x lying between 0 and 1 and y lying between 0 and 2. So the first thing that we're going to need to do is we need to convert this ds, which just stands for like a little surface element on our surface, into something that we can use in terms of x's and y's. So we want to convert our ds into a dx dy. So we're going to need some partial derivatives. This is pretty straightforward, so we can go straight in. I'm going to just write down ds is equal to partial g with respect to x, so that's going to be a 1 squared plus partial g with respect to y, it's going to be a 2y, I want to square that, plus 1 dx dy. And so we can put this all together and we're going to convert our original surface integral into a double integral of f of xy times by our surface element, which is 2 plus 4y squared. Okay, and dx dy, and at the moment, let's just have a look, we're going from 0 to 1 and from 0 to 2. All right, and then we can think about how to work with this, this a bit better. How might we want to do this? I'm having a look at the textbook here, which is helping me do this quickly, but you could think about this. We could split this up. Okay, so I'm probably going to do y first, so do a switch around. And you could take out a root 2 here out of the square root, so that you'd get dx root 2 and integrate y 1 plus 2y squared. And if you do that, so I would probably do integration by substitution or something like that. You can work through it to do the y bit. The dx is straightforward. Spend a bit more time practicing your integration, and what you should end up with is something like this. Okay. I'm not spending too much time on the integration here. The key thing here is essentially what we've done is we've gone from a surface integral up here, which was not clear how we would solve that, and turning it into a double integral, which, assuming we know how to do the integration, works fine. All right, so that was the surface integral for a scalar vector field, but a scalar field, but we can also think about surface integrals of vector fields. Now in this case, because a vector field is a vector, we're going to be looking at integrating the vector field, which is doing that spiky vector thing, and thinking of the surface as having an orientation. So we're looking at how the vector field intersects with that surface and its normal. So what we end up with is something that looks quite a lot similar to what we just had, but we've got, so here's our vector field, and we're dotting it with a surface element. So we're imagining that if our surface is doing something like this, and this is a little surface element here, that it has an orientation, it has a normal like that. So we're thinking of this ds as a vector, a little kind of vector that has a direction. So we basically, that's the ds of our surface, and we're imagining that maybe our vector field is doing something like this, and we're looking at the dot product between the two over this little surface element, and then we're going to add that up over the entire surface. So one of the things that makes this, that adds a little twist to this compared with the scalar field version, is obviously our little surface element has two possible normal vectors. It either has one pointing up or one pointing down. So when we're doing these problems, we need to just think about, are we wanting to measure the vector field coming out of the surface, in which case we want our normal vector to go up out of the surface as well, and we see how much of our vector field goes in that same direction, or are we wanting to measure going into the surface, in which case we'd use the downward normal. So there isn't an answer, a quick answer to this. You just have to read the question and figure out which way it's going. But we'll do an example and you'll see. So we can do exactly the same thing as we did before, and we end up with something that looks quite similar. So here, instead of having just the magnitude of the cross product, now we're actually calculating the little normal vector here to our surface. So this is a little vector, and we're going to dot it with our force and integrate using du dv. So this is imagining we've got the same kind of parameterization. And our orientation is captured here, where you have to pick whether you want to use plus or minus, which is essentially looking at this vector here and saying, do you want the one that's pointing out of the surface or down from the surface? But the maths comes out being almost exactly the same, and we end up again with being able to convert into a double integral that we can do. So we'll look something like this, and here a, b, and c are the same as I had for the previous version over there. And again, we're picking orientation here depending on which way you want to go. So just to summarize this, so this version over here is for the most general parameterization of the surface that you have in U's and V's, but you can play exactly the same trick as we did before by saying, okay, suppose that I just have my surface in terms of x and y instead of parameterized complicated U and V. Do the same calculations that we did, converting from U and V to x and y, and you'll find out that now, for this vector field case, we have our little surface element vector looks like this, which is the vector equivalent of the thing that we found over here. So here we have, so where you really want to look is up here, where we have our dr crossed with our dr by du crossed with dr by dv. And we're calling that, because we're now thinking in, so the way we're working with this, we're thinking of our surface as a g of x, y, z equals 0, a surface, a level curve. or a level surface. And the equivalent of what we just saw there is that our surface element is given by the gradient of g divided by the third component. So this is the z component times dx dy. So the notation looks a little bit different, but it's almost exactly what we worked out previously. And again, we have to pick plus or minus depending on which way we want our surface element to point. Do we want it out or in? So this is much easier to see if we do an example. So let's do one straight away. So we've got a vector field, z in the I direction plus x squared in the k direction. And we want to find the flux upward through the part of this surface lying above the square defined by this bit, like so and like so. Okay, so because we have our surface in terms of x, y, and z, we don't have to go and do the full complicated route, which is this bit over here. We can go and do this route over here. So let's work through the various bits that we need for this particular problem. Okay, so we're going to say that our surface here is our g, and remember we set this equal to g of x, y, z is equal to 0. So I need my z on and my x and y all on one side, put it all equal to 0, and that's equal to g. So my g is going to be equal to z minus x squared minus y squared. So if I take the gradient of that, that's going to give me a minus 2x in the I direction, minus 2y in the j direction, and a 1 in the k direction. And the third component of my g, sorry, the third derivative is going to be equal to 1. So up here, over here, this is the z component derivative. I should have written there. Okay, so putting that all together, let's just get the gradient of g over g first. So we've got a minus 2x I minus 2yj plus k, and that's all over 1. And going to be dx dy. And the thing that we need to think about is this going to be plus or minus? Well, the thing to think about is you've got your x, y, and z, and whatever your surface is that you're interested in, you want upward through that part of the surface. So if you're going to be pointing upwards, you always need to have a positive component to your z component. So what we want to take here is whichever sign here ensures that our z component is positive. And so that tells us that we should pick the positive version. So we're not going to take that. Okay, so our ds is minus 2xi minus 2yj plus k hat. And so we can put this all together. Okay, so we need to find our flux here. What we're wanting is flux, which is the integral over the surface of our vector field dotted with our little surface element. And what we've found here is our surface element is this thing here. So we want the integral over our surface of our flux, which is this, dotted with ds. So if we work out this dot product here, so remember this is our flux, rather this is our surface element. If we work out that dot product, we're going to get our integral over our region R, which is this here. Oh, let's have a look. Minus 2zx. There's no y component, plus x squared dx dy, and then we remember that our z is equal to x squared plus y squared. So we've got this. And finally, we need to think about the limits of integration here. That is in fact given in the problem. We're lying above the square r defined by x lies between -1 and 1, y lies between -1 and 1, and so we can put these in, whoops, not 0. All right, and you can do some integration practice there, and what you should end up with is 4/3. Okay, so just to kind of summarize all of this, what we've figured out is anytime we're wanting to do an integral over a surface, we are looking at something, an integral that has a little surface element ds, and we always need to, in order to be able to actually compute the integral, turn this into some sort of dx dy, which usually has a scaling factor. And if we're looking at surface integrals for scalar fields like this, then our ds is going to be something like this, where the g, our surface, is something like z is equal to g of xy. On the other hand, if we're looking at vector fields and we're wanting to find the surface integral there, then we parameterize our surface like so. So we write it as all our x, y's, and z's on one side equals to 0, and we put that equal to our big G, and our surface element, which is a little vector, is given by this thing over here, and you choose the plus or minus depending on whether you want it to point out or into the surface. Okay, and we've looked at a couple of examples. So see if you can do a few more examples of these, just get the hang of it, because we're going to need this particularly when we talk about Stokes' theorem.